Hello everyone, welcome to this channel. My name is Amna Ibrahim and in this video we will take a look at what autoencoders are very briefly and observe their potential in anomaly detection. This video assumes that the viewer has an understanding on the basics of neural networks. This video will be split up into four main sections. We will first briefly talk about autoencoders, what they are and their applications, as well as their application in anomaly detection, which is the topic of our video. We will then briefly talk about the dataset that we will be using during this tutorial and our implementation workflow, and finally, we will take a look at the code. The tools you need for this tutorial are very minimal. You don't need to install anything onto your laptop or PC, as we will work on Google Colab using Python and some libraries like Pandas and TensorFlow. So let's get started. What are autoencoders? Autoencoders is a type of feed-forward neural network that is trained to attempt to copy its input to its output. At first glance, it may seem as it is not very powerful, as why would we want a model that copy the input to its output? But when we learn how they do what they do, it becomes a very powerful model. Autoencoders do what they do through encoding or compressing the input data into a lower dimensional state or code. And then from that lower dimensional state or code, they reconstruct that output from this representation. So essentially, this lower dimensional representation contains the most essential features needed to reconstruct the original form of the input data to its output. An autoencoder is comprised of three main components: the encoder, the code or the bottleneck, and the decoder. The encoder comprises the encoder layer is the layer that encodes the input into a compressed representation through reducing the dimensionality of data. As you can see from the image, a typical autoencoder's hidden layers contains progressively lower numbers of nodes than the input layer. This is because the data will travel through the encoder layers, getting compressed at each layer until we squeeze it into fewer dimensions that will pass through the bottleneck, which is the next layer, or code. The bottleneck or code will contain the most condensed and compressed representation of the input. It is both the output layer of the encoder network and the input layer of the decoder network. The fundamental goal of the design and training of the autoencoder is discovering the minimum number of important features or dimensions needed for effective reconstruction of the input data. The decoder is also made up of hidden layers that get progressively larger in terms of the number of nodes until we reach the output node. And this is because we're trying to decode the encoded representation of the data back to its original form. This autoencoder model learns with the help of a loss function, which measures the difference between the reconstructed output and the ground truth input. And when we measure this difference, it gives us the measure of effectiveness of the autoencoder we've just built. That difference between the output and ground truth or input is called the reconstruction error. But why are autoencoders useful? Autoencoders helps us discover the hidden variables and parameters that is in the input data, and we do that through passing it through a bottleneck, which forces only the most important features to pass through before it reaches the decoder. And this essentially forces the encoder to learn to extract the most important information required to accurately reconstruct the original input. It can be used in many applications, such as dimensionality reduction and feature extraction. But in this video, we will explore it in the light of anomaly detection. So how can we use it for anomaly detection? As we've briefly touched on, an autoencoder is trained to minimize the restriction error. So if we have a dataset of a device that is behaving in a normal condition, we can train the autoencoder to realize the normal operating behavior. Therefore, hypothetically, when we try to reconstruct input data that is abnormal, the autoencoder will fail to do so because it will be totally different from what it was trained upon. And therefore, the reconstruction error will be very high. So we can use the reconstruction error as the indicator for anomalous behavior. Let's test this hypothesis out and see the potential of autoencoders for anomaly detection. So let's lay down the plan of action for testing the hypothesis. First, we need to install and import the necessary libraries as well as the dataset. Then we will visualize our dataset. We will pre-process that dataset, engineer the model, train it, evaluate the performance of our model, and save it. Before jumping onto the code, let's take a look at the dataset that we will be looking at during this tutorial. We will be using the engine fault.db dataset, which is produced by the research article displayed. I will be linking the paper and dataset in the description if you'd like to read more. The dataset observes the intricacies of automotive engine diagnostics, and it labels the data of normal and fault scenarios. These scenarios are captured into 4 categories. We have the no fault or the normal operation, which is indicated by a value of 0 in the label column fault. And then we have 3 types of faults. We have the rich mixture fault, which is indicated by 1 in that column, the lean mixture fault, which is indicated by 2 in the label column, and the low voltage fault, which is indicated by 3 in the label column. As for the model that we will be building, we will have an input size of 14, as the input data has 14 features. The dataset contains 14 distinct variables. And as we want to reconstruct that data, the output will also have 14 layers, or 14 nodes. In the encoder part of the model, we will have a fully connected layer of 10 nodes that aims to compress the data such that we can find the most important features, and then it will be passed to the bottleneck or the code part of the autoencoder, which will be made up of 3 nodes. Then, as for the decoder network, we will have a fully connected layer of 10 nodes to reconstruct the encoded information to its original format. As for activation, you can see from this image that we have used ReLU in the hidden layers of the encoder and decoder network. So first and foremost, make sure that you connect to a hardware accelerator or GPU, as we will be training a model using Google Colab, and I'm choosing the T4 GPU. So I'm connected to it. Then we will need to install the libraries, which are matplotlib for visualization, pandas and NumPy for dataset manipulation, and TensorFlow and Keras for building the model and training it. Then when we take a look at the dataset, which I've saved into my Google Drive, and you can go ahead either save it to your Google Drive and read it from there, or upload it into this temporary storage space that will get resetted. I prefer that you put it into your drive and visualize the first few rows of the dataset. We can see that we have about 15 columns with the label column as the first column. And we can see that the first few rows are of the label 0, meaning that this is the normal operation conditions for the engine we're taking a look at. Now, when we take a look at the different labels in the fault column, we can see that we have 4 distinct labels indicating different types of category of data, whether it's a normal, which is represented by 0, or abnormal, which is 1 or 2 or 3, dependent on that type of specific abnormal operating condition. Now, it's always good to take a look at the data you're working with, visualize it in whatever ways that makes you understand the data more. So when we look at the amount of times we have the different types of faults, we can see that 28.6% of the data is healthy data, whereas we have lower percentages for the faulty data. But when we look at the normal operating conditions data, it only makes up 28.6% of the data set, whereas the faulty data makes up way much more than the healthy data set. So we will work with a small data set of 16,000 rows when training the model. It's also very good practice to look at the data set and search for any null values that you can either remove or fill it in. In our case, we don't have any null values, and therefore we don't need to fill it in. If you'd like to learn the essential tools of data pre-processing or data manipulation using pandas, I've created a playlist for that. For your reference, I will be linking it down in the description below. Now let's take a look at the dataset statistical description. We can see that we have a total of 55,999 rows for all columns, meaning this is the size or the row size of the whole data set, and we have 14 or 15 columns, including the fault. And these are the minimums, the maximums for each column, as well as the standard deviation and mean, and the percentiles. As we're trying to get the encoder to realize what healthy engine data looks like, we don't need the faulty data. So the first step is to create the healthy dataset that we will be training the model for. And that's exactly what I will do here. We just created a dataset of the size that we saw over here for the healthy dataset, 16,000, and the columns are 15, including the fault. Now, if we remove let's also check if we only have healthy data. So we can see that the unique values of the column fault is 0, indicating that we only have the healthy data available, or the no fault data. As we will be training the model to understand the patterns within the input features, we don't need the label column to understand the behavior of the data. So we will drop that, and when we take a look at the shape of the data set, we have 14 columns now. And as we will be training the model, we just need the values, and this is what this essentially does. The next step would be to train and test split. The split we have here is of 20%, okay, of the data set will be for the test, and the rest will be for the train. It's always good practice to normalize the data. Normalization of data means that all features of the model are brought to a uniform scale, such as the range between 0 and 1. When we take a look at the data again, we can see that there are some features that have values in the range of 3. Let's take a look at this one. We can see that we have data with the maximum being like 3, and then we have data that has, values ranging from a minimum of 2 to 1,000. So it's always good to normalize this data. And this is what we do over here. There are many advantages to using normalization. And in our case, we will be bringing all the data to a uniform scale between 0 and 1. The reason for that is that we don't allow for bias in the model towards large numerical values. If we don't use normalization, features that naturally have higher numbers could contribute more to the model's prediction than others. It would also make training more uniform and fast because there are no large jumps in the numbers that could lead to irregularities. We will be using the min-max scaler as a form of normalization, as it will scale the numbers from a value between 0 and 1. And it essentially does that through using the maximum and minimum values of the features or the columns to normalize the data to a value that is from 0 and 1. And the main advantage for this scaling technique is it's simple to use, and it also has an ability to retain the relationship between data. To normalize, the dataset will first fit the pipeline of the min-max scaler to the training dataset, and then use that information to transform both the test and train dataset based on the min-max values of the training dataset. Okay, now we come to the important part of building our own model. First and foremost, let's first acquire the input dimension, which will be the size of the features. And so we will get that from this statement, and then we will build the model. We will be using a sequential model, and first and foremost, we will first need an input layer of size 14, and then we will create a encoder layer of 10 nodes, a code layer of 3 nodes, and a decoder layer of 10 nodes, and finally an output layer that matches the input dimension of 14. And when we go ahead and visualize it, we can see that it matches what we've discussed previously in the slides. Then we will use a loss that will be calculated using the mean squared error and an optimizer of Adam. And then when we take a look at the summary of the model, we can see that this is the summary of the model. We have a dense layer, which is the encoder layer of 10 nodes. We have the code, we have the decoder, and the output layer, as well as the input layer that's not being shown over here. Now, we will specify the batch size and the epochs to train the model. The batch size that we will be inputting to the model in each training epoch is about 1026. And epochs in machine learning refers to one entire passing of training data batch through the algorithm. So we are passing a batch size of 1026 each time, or in each epoch, and we have about 200 epochs, so 200 passings of input data that is of a batch size of 1026. Now, when it comes to training the model, you could see that the X value for model.fit is the transformed or normalized training data, and the labels will be the training data itself. Because remember, the autoencoder is trying to completely reconstruct the input data. So naturally, the label data would be the training input data itself. And similarly, we have defined the same for the validation data, which we have specified here to later on, when we are looking at both the validation and training loss, understand whether or not the model is underfitting or overfitting. So we've also specified the validation data to be the test transformed as the input, and the label data that we're trying to compare is the test transformed data set itself. We've also defined the epochs and batch size. And we will be storing all the model's parameters as well as the model's history into the variable history, which will contain all of the training history that we will be using later on to visualize the losses, to just take a look at the model's performance. And so it will start to train, and we'll give it some time to train. Now that the training has finished, let's visualize the history of the training, more specifically the loss, and compare the losses between the validation loss of the validation data and the training loss. And we can see that there isn't much of a difference between the validation and training loss during the whole, training process, which means that the model has generalized based on the data and hopefully hasn't overfitted or underfitted. So let's test our hypothesis of whether or not anomaly detection is possible with autoencoders through testing the model's performance on the faulty data, as we've now built a model that fully understands the features of healthy data. And what we will do is we will create a dataset of fault type 1 and do the same pre-processing that we've done for the healthy dataset, which is dropping the fault column and normalizing the data. And this is exactly what we have done over here. And then we will first predict the reconstructions for the faulty transformed data, and then calculate the mean absolute error for that reconstructions. The reason we are doing that is because we want to compare the mean absolute error for the reconstructions of faulty data and see the difference between that of the faulty data and the healthy data. And hopefully, it should be at least 50% higher than that of the healthy data. Because remember, the model is trained on healthy data, and hypothetically, it should find it difficult to reconstruct unhealthy data. And so when we find the reconstruction errors or the mean absolute error for the train and test dataset and compare them, what we find is the reconstructions for the test data is the same as the train data for the healthy data. However, for the anomalous data, we can see that it's about twice as much as that of the train and test data of the healthy dataset. And this verifies the hypothesis of autoencoders having a potential in anomaly detection. So naturally, the next step would be to find the suitable threshold that we can set for the reconstruction error to flag that input data as anomalous. But we won't be doing that in this video. Now let's save the model. And to save the model, we just say model.save. We specify the path in our Google Drive and name the model. I've named it Autoencoder, and I'm going to use the H5 serialization. And when we run this and go to our Google Drive, we will see that we have successfully saved the model to load later on. Thank you for watching this video. I hope you found it useful, and I hope you've learned about autoencoders and their potential in anomaly detection. If you found this video useful, consider subscribing or supporting the channel through Patreon, which the link for it is in the description below. I've also linked the code in the description below so that you can try it out by yourself with different datasets, as well as the dataset that I've used. And as always, thank you for watching.